Well, good evening, everybody, and welcome to this evening's inaugural lecture. We're delighted to see so many visitors and so many friends of the department and people here to support Bassam in this lecture. It was almost 10 years ago that I learnt that I was to join the department here at Imperial. And of course, one of the things that you do in a situation like that is you make inquiries about the people you're joining, the soon-to-be colleagues, to find out what the views are. And the view I got on Bassam was there's this very clever young lecturer in structures, and do you know, he's the person that got the highest ever score in the MSc in structures. And of course, as I've been here these past 10 years, one by one, these facets of the description have changed. When I arrived, he was promoted to a readership. Shortly afterwards, he delighted in saying, I'm not quite as young as you might think I am. You know, I'm a little bit older and more distinguished. And then, of course, somebody took away the exam score. We had a student that got, in fact, two students in the same year that actually got a higher score. And just recently, Bassam was appointed to a chair, so he's now Professor Izzuddin, but he's still very clever. And I'm sure he's going to demonstrate that tonight in the best possible way, because Bassam has used his intellect really to explore some extremely complex phenomena in the field of structural engineering. He studied those in a rigorous way, and just as importantly, he's looked for ways to communicate the results so as to both aid an understanding in the subject area and to ensure that the outcomes will be of assistance to furthering the practice. So I'm delighted to invite Professor Bassam Izzuddin to come forward and deliver his inaugural lecture tonight. Bassam.
Right, I hope I can live up to this promise. Mr. Chairman, Professor Dowling, ladies and gentlemen, friends and colleagues. I start with the idea that structural engineering is about bringing order in an otherwise chaotic environment. And when we talk about order, there are many descriptors. But the keywords are predictability, simplicity, safety, and comfort. Towards this end, structural engineering, supported by codes of practice and regulations, has to overcome numerous forces of chaos, including environmental actions, accidental actions, imperfections, and human factors. The evolution of structural engineering over its long history can be seen as the result of the desire by society for order in the face of new or increasing forces of chaos. But of course, there are no absolutes. Order and chaos are a matter of acceptance, a matter of scale. What may appear chaotic at a certain physical scale can be very ordered at another, for steel structures and for concrete structures. Order and chaos are also relative to the time scale under consideration. Consider that we know that the next impact of a major asteroid will occur in 100 million years, plus or minus 100,000 years. Now, that's very good prediction accuracy. But if the margin of error remains 100,000 years until then, the event when it occurred would appear to be random, unpredictable. And often, both the physical and time scales need to be considered. Often, one needs to look at the bigger picture to find order in good time. However, when it comes to engineering, the question of order and chaos is largely a matter of response. Consider this two-link, two-mass pendulum, which is a simple structural system in physical terms. Its response under moderate oscillation is equally simple, predictable. This predictability is also reflected in the fact that a slightly different tip mass does not lead to a drastic change in the response. Now, if we look at the same pendulum, but started from a horizontal position, the response over the first 8 seconds is reasonably predictable. This is the response of the original pendulum and the pendulum with the slightly smaller tip mass. But after 30 seconds, it becomes chaotic, unpredictable. It's a simple structure, but it is actually chaotic. A minor uncertainty in the tip mass leads to completely different predictions. We can now use this example to distinguish between science and engineering. Science deals directly with chaos and tries to find order in it. It looks at a chaotic system to find what can be predicted and the underlying principles. Looking at our example pendulum, the circular path traced by the middle mass, and indeed the upper limits of this path, are also predictable. However, the path of the tip mass is unpredictable, chaotic. But amongst this chaos, the envelope within which the tip mass moves is actually predictable. Engineering practice builds on the achievements of science and research and deals only with what can be predicted. It designs order by ensuring that the predictable is acceptable. If this were supposed to be a typical civil engineering structure, carrying weight in the horizontal position, like people, its predictable envelope would be unacceptable, except perhaps in Disneyland or maybe in Guantanamo Bay. An engineer would typically add vertical members, and if they studied with us here, they might even be creative and add a couple of braces against sway movement, and in the process, they would ensure that what can be predicted is also acceptable. Looking now at real structures, Ronan Point was designed properly by 1968 standards. However, a gas explosion on the 18th floor caused failure of the outer wall. The top floors failed, and this led to progressive collapse of a whole corner of the building. By today's standard, this would be a badly designed structure. We now know better. Still, current design practice for this type of failure is not satisfactory, as it is not based on predicted performance and acceptability. Contrast Ronan Point with a more modern building in Portugal, which also sustained a severe explosion last year. While there was widespread damage to the facade, the structural damage was localized. There was no progressive collapse. Now, whether this was by design or luck, this is the type of order the structural engineers should be providing by design. Looking at another type of extreme event, an earthquake, the building in the center was designed to resist earthquakes and constructed accordingly. Maybe the surrounding buildings were relying on divine providence more than design or good construction. Now, coming to designing structures, in such a situation, an engineer works with representations of the structure, the applied actions, such as gravity, wind, fire, explosion, and earthquakes, and the structure's response to such actions. The engineer then seeks to evaluate the acceptability of the response. Now, the closer each of these representations is to reality over the intended life of the structure, the better the design. Designers use various prediction tools and QA procedures to approximate the real structure, the applied actions, and the response. Importantly, the overall adequacy of the design depends on the degree of predictability in each of these areas. Accordingly, structural design cannot deal directly with unpredictable events, such as malicious or terrorist actions. Structural failure in such cases should not be seen as the responsibility of the designer, unless failure is disproportionate to the cause. My work has been concerned with response prediction, specifically simplified and detailed analysis methods, and that's what I'll be focusing on for the rest of this lecture. You will be glad to know. Developments in response prediction have progressed in tandem with the evolution of the concept of failure. Let's consider a structure under increasing static load. There is normally a range of load over which the response is linear. Beyond this range, material damage, like yielding of steel, gradually spreads over the structure until a strength limit is reached. Subsequently, the structure undergoes large displacements until it breaks or fails. Here, different structures can have different types of response. Brittle structures can fail at relatively small displacements, while ductile structures take much more displacements before failing. Some structures harden, and others soften. Now, in the early days of modern structural engineering, I'm talking here early 19th century, the onset of material damage was considered to be detrimental. It was then suggested that linear elastic analysis was all that an engineer required. Actually, any design falling outside the predictable elastic limit was associated with failure. Currently, linear elastic analysis is still used extensively in design practice, but its application is more elaborate. We now use component strength instead of the onset of material damage as a failure criterion. Still, this criterion does not consider the additional safety in redundant structures, for which the strength limit can be much higher than the elastic limit. The strength limit has been recognized over the past 40 years as a more appropriate criterion than the elastic limit. Developments in rigid plastic and small displacement elastoplastic analysis helped in its increased adoption. Nevertheless, this criterion has disadvantages. It is conservative for hardening structures. Also, it does not recognize the benefits of ductility under extreme dynamic loads. So the most consistent criterion with actual structural failure is based on the ductility limit. And for dynamic loads, this criterion simply reduces to checking the maximum dynamic response. Ductility-based design has gradually been gaining acceptance in several areas of structural engineering, such as earthquake and blast-resistant design. However, its increased application requires both detailed and simplified response prediction methods that account for material damage, which means material nonlinearities, large displacements, geometric nonlinearities, as well as structural failure. Obviously, these methods must be validated against real structural behavior to ensure predictability in design. So how do we go about predicting the response of structure? Invariably, we use a divide and conquer approach. The response of the structure is assembled from the responses of its individual parts, such as columns, beams, braces, slabs, and so on. I'm showing here a partial model of a building. In detailed analysis, similar models are used for columns, beams, and braces. Looking at a beam, the most effective modeling approach is to further divide the beam into what we call finite elements, which interact with each other at the nodes. The model shown uses one-dimensional elements, where divide and conquer also is applied here by relating the deformations along the element axis to the nodal displacements. And further division is made at the cross-sectional level if we require an accurate representation of the spread of material damage. A more accurate but a more demanding approach is based on the use of two-dimensional elements. Notice the increased number of nodes for modeling the same part of the beam. These types of elements could be required to model things like local buckling or to model challenging configuration, challenging forms, such as cellular beams. Here again, the division process continues at the element level by relating the deformations within the element to nodal displacements. Now looking at the slab, this is often modeled with two-dimensional elements. However, if the slab thickness is not uniform, more demanding three-dimensional elements may be required. Again, notice the increased number of nodes to model the same part of the structure. Now we come to the question of accuracy and efficiency in response prediction. If we compare civil engineering structures to mechanical engineering or aeronautical engineering structures, we find several fundamental differences which also impact on response prediction. This list includes the use of less predictable material, less quality control, less time for design, and greater uncertainty in action. Therefore, compared to mechanical and aeronautical engineering structures, response prediction for civil engineering structures has to maintain a more practical balance between accuracy and computational efficiency. When using finite elements for detailed analysis, consideration should be given to computational demand. 1D models tend to be the quickest to process, are very similar to a fork of spaghetti. Two-dimensional models are also manageable with the right equipment, while substantial three-dimensional models can seriously harm your typical computer. Clearly, one-dimensional models should be used for response prediction if possible. Two-dimensional models should be used only if necessary, and three-dimensional models should be reserved for the very special occasions. I'll now give some highlights of my work on response prediction for extreme loading, including rotations and geometric nonlinearity, advanced one-dimensional and two-dimensional elements, validations for extreme loading, and simplified modeling. Starting with rotations, everywhere you look around you, there are rotations. Even the act of looking around involves a rotation. Rotations are crucial for the solar system. Therefore, they are an important concept for astronomy. Closer to home, rotations are an essential idea in many fields of science and engineering, including power generation, like hydropower, biomechanics, the mechanics of walking straight while moving your arm up and down, and transport. Indeed, rotations are the root cause of geometric nonlinearity and the associated complexities in structural behavior. However, once this seemingly negative approach is appreciated, it can actually be put to positive use. In fact, it can bring order, allowing simplification of much of the complexities in geometrically nonlinear analysis, including buckling analysis, large displacement analysis of frames, and large displacement analysis of plates and shells. So how can rotations be used to simplify buckling analysis? I'll focus here on predicting the vertical buckling load for an elastic frame as a special case of geometrically nonlinear analysis. Initially, in order to cause the frame to sway by a small displacement, du, we need to apply a small lateral force, dF. The ratio dF by du is the lateral stiffness of the frame, and the larger this value, the more difficult it is to push the frame. Now, if the frame is carrying vertical loading P1, its lateral stiffness reduces, and the larger the vertical loading, the smaller the lateral stiffness. Buckling finally occurs at a vertical load P critical, for which the lateral stiffness becomes 0. At this load, the frame starts to sway without the need for a lateral force. Considering the lateral stiffness in more detail, it consists of two parts, basically what we call the material stiffness, which depends on the material, obviously, and the geometric stiffness, which is not related to the material at all. It simply depends on the applied loads and the internal stress state of the structure. For compressive axial forces, the geometric stiffness is negative, and buckling occurs when the geometric stiffness equals the negative of the material stiffness. Now, the material stiffness can be easily obtained from principles of linear analysis, which are familiar to most engineers. On the other hand, the geometric stiffness is a more abstract concept. Its evaluation using the conventional expression is not as straightforward as it looks. It requires knowledge of nonlinear kinematics of the problem, at least to second order. Now, in a moment of serendipity a few years ago, I found out that the geometric stiffness can also be evaluated from linear analysis using equivalent rotational springs which are associated with individual elements. The rotational stiffness for each spring is equal to the axial force in the element times its length. So for this frame, the geometric stiffness is obtained from two equivalent rotational springs associated with the two column elements, because the beam does not have, in this case, any axial force in it. Good approximation is obtained with two springs, and improving accuracy can be achieved with more elements. In the limit, the geometric stiffness is exactly obtained with distributed rotational springs, for which the rotational stiffness per unit length is equal to the axial force. This analogy has significant benefits. It allows a quick approximation of the buckling loads with an assumed mode using only linear analysis principles. In this case, for this example structure, 1% accuracy is achieved in the buckling load factor. It is also applicable to discrete as well as continuous problems. For this continuous arch, distributed equivalent springs can be used to evaluate the geometric stiffness. And finally, it enhances the understanding of the main parameters affecting the buckling phenomena. Referring to the lateral torsional buckling of this beam, the lower tensile part would have positive stabilizing equivalent rotation springs, whereas the upper compressive part would have negative destabilizing springs. This explains why the longitudinal rotations in the buckling mode are greater in the upper than in the lower part of the beam. Moving now to large displacement analysis of frames with one-dimensional elements, consider a one-dimensional element before deflection. The element can be subjected to 3 component translations at each node, which may be large. In addition, 3 component rotations can be applied at each node, which may also be large. Now, unlike translations, rotations in 3-dimensional space are problematic. If large rotations are applied about fixed axes, then the result is order dependent. Consider this block and what happens to it when we subject it to 2 rotations of 90 degrees each about the same axes each time, but in different order. So here the first rotation is about the x-axis, the second is about the z, and here is the other way around. Same rotation, same axis, but different order. Now, we see this block rotating this way, whereas the other block obviously rotates and ends up in a different orientation. So we need to address this issue with nodal rotations, specifically when we are dealing with large rotations. And in order to address this issue, the order of rotations about fixed axes must be assumed. I adopted an alternative definition, which I developed with a simple transformation matrix, and which is based on combining the rotation components into a single rotation vector. The resultant rotation is then applied about the vector axis, avoiding order dependency. In any case, rotations are not only at the nodes. In fact, the element code rotates even if only translations are applied to the nodes. Now, relating the deformations within the element to the original global freedoms is very problematic in large displacement analysis. And I'm denoting this by showing the cross-section moving slowly along the length. Yeah? A much more powerful and simple approach is to relate the element deformations to local freedoms in a reference system that follows the element as it deforms. And here I showed it already as moving fast along the element length. What is then required is to relate the local nodal freedoms to the original global freedoms, which is relatively straightforward. Okay? This is the essence of the co-rotational approach which I developed for a range of one-dimensional finite elements. And before I leave the issue of rotations in frames, I must talk about moments. These are different from the common meaning, moments in time. In mechanics, a moment can be a load applied externally to a beam. In large displacement analysis, when the rotations can be large, we have to distinguish between different ways of applying external moments to a structure. A quasi-tangential moment is generated by a pair of equal and opposite forces, while a semi-tangential moment is generated by 2 such pairs. Now, these moments behave differently under large out-of-plane rotations. A beam can also have internal moments, bending and twisting moments, which are stress resultants. And as if there wasn't enough confusion between moments in time and moments in mechanics, confusion spread to external and internal moments. And prominent researchers perceived some similarity between the way internal and external moments were generated. And many embarked on a mission to classify internal moments according to the classification of external moments, wondering whether the bending moment is a quasi-tangential one and whether the twisting moment is a semi-tangential one. They wrote numerous papers in leading international journals disagreeing with each other about the internal moment classification. And that was fine, at least with me, until one Australian group insisted in the Journal of the American Society of Civil Engineers that they had discovered the correct classification and that any analysis method which did not incorporate their classification was incorrect. At this point, I felt that I had to intervene because I did not use any classification, let alone theirs, and my methods performed very well. So in a paper on related conceptual issues, I pointed out that external moments worked with rotations and were affected by them. However, internal moments could not care less about large rotations. They worked with curvature and with the rate of twist. I also demonstrated that classification of internal moments was unnecessary, nonsensical, and should be avoided for the sake of both simplicity and predictability. Now, looking at the performance of a couple of one-dimensional elements that I have developed, the first is a quartic element, which can represent the large displacement elastic response of beams and columns with one element per member. This is the classical problem of a frame dome subject to a vertical load at the apex. As the load is increased, the dome deflects vertically until it buckles in an asymmetric mode. The load deflection response clearly shows the load at which the structure buckles and that the subsequent large displacement elastic response is stiffening. Importantly, the predicted response with 2 elements per member is virtually identical. This highlights the accuracy of the quartic formulation in modeling nonlinear elastic frames with 1 element per member, which is important for adaptive analysis, as I will discuss later. The second formulation is a cubic one, which can model the large displacement elastoplastic response of thin-walled beams and columns, including lateral torsional instability. Elastoplastic analysis is much more demanding than elastic analysis, and therefore several elements are normally required for each member, typically 6 or more. Here, an I-beam is modeled using 10 one-dimensional elements, and its elastoplastic lateral torsional buckling under end moments is considered. Comparison is made with the more general 3-dimensional elements, where a similar deformed shape can be observed. Considering the detailed load deflection response, the developed 1D element clearly provides very good accuracy for this type of problem, where cross-sectional distortion and local buckling are not an issue. Importantly, however, if you look at the computing demand, the 3-dimensional elements require over 300 seconds. With the 1-dimensional elements, on the other hand, we can achieve similar accuracy in only 0.3 seconds, a demand ratio of 1,000 to 1. So clearly, 1-dimensional elements have an important role to play in structural analysis. Moving next to plates and shells, and looking at a typical 4-noded 2-dimensional element, like the beam element, it is very helpful to relate the element deformations to local freedoms defined in a corotational system following the element. The problem is how to define this local system in the current deformed configuration. Other researchers proposed an approach based on a zero-spin criterion, which is intended to work more with large strain problems. This is relatively complex and can require the solution of nonlinear equations just to locate the local system. I proposed simpler approaches, which work very well for civil engineering structures. One of these defines the local planar axes simply as the bisectors of the element diagonals. And the nice property about this is that the local axes are already orthogonal, and they follow the element in its deformed configuration. The next issue is defining the rotation of the nodal normal. Unlike one-dimensional elements, here only 2 rotational freedoms are required to define the rotation of the nodal normal. Others have proposed the use of actual rotations, which can become complicated for large rotations. Instead, I proposed a much simpler and more efficient approach, where the 2 smallest components of the normal are directly used as degrees of freedom. In terms of performance, consider this slab, which is fully restrained along one long edge, simply supported along the 2 short edges, and free along the 4th. Assuming elastic behavior here, the large displacement response of the slab under a uniformly distributed load is obtained with the developed corotational elements. An important feature of the developed corotational approach is its insensitivity to the size of the load step. This makes it insensitive to cumulative round of errors, which could be an issue in dynamic analysis. The previous results were obtained with 20 steps, and identical results are obtained with only 4 steps. Now, considering the slab to be restrained from pulling in along the simply supported edges, the response is much stiffer, dominated by what we call membrane action, which is a form of geometric nonlinearity that is very important under extreme loading. And I include my brief description of the work on detailed response modeling with composite floor slabs. These are just one of the many examples of the evolution in structural form for civil engineering construction. They have numerous construction and performance benefits, which I cannot go into now. What I want to highlight is the modeling challenge that they pose, particularly in relation to geometric orthotropy, the fact that they have different cross-sections in the two orthogonal directions. If we consider a typical rib, to formulate a two-dimensional element, we need to relate the displacements within the rib to the displacements along the reference plane. If we adopt the conventional Reisner-Milne hypothesis, which was proposed for uniform thickness plates, this requires that the normals remain straight after deformation. This is fine for uniform thickness plates, but this is inadequate for ribbed slabs. For example, it is difficult to imagine for this stretching mode how the rib could also be stretched at the bottom, given that there is no material either side. The conventional hypothesis becomes unrealistic for deformations involving stretching and bending in the transverse direction, and these can be very significant under fire scenarios. So to deal with this problem, I proposed a modification of the Reisner-Milne hypothesis where additional rib freedoms are incorporated into a two-dimensional formulation such that the normals do not have to remain straight. And to see how well this works, let's consider an elastically supported rib slab under uniformly distributed loading. The slab is modeled with the proposed two-dimensional elements and with the more general three-dimensional elements for comparison. The 2D model provides excellent prediction of the response in comparison with the three-dimensional model. What is striking, as you'll see next, is that this accuracy is achieved at great computational efficiency. The 3D elements required 22 hours to perform this analysis, while the 2D elements perform this analysis in only 2 minutes, a demand ratio of around 700 to 1. So if we can, we should use two-dimensional elements. I've sketched some of my main contributions in large displacement and rotation analysis of frames and plates, and I've had to skip over a lot of complementary modeling work that I undertook on materials, connections, interfaces, and advanced solution procedures. Now I return to the original idea that structural engineering and design are concerned with evaluating what can be predicted. This is the real question that any response prediction model should answer before it can be applied with confidence. I'll address this question of validation for my modeling work, referring specifically to 4 areas of structural engineering: offshore jackets, buildings under fire, failure of floor slabs, and blinding struts. Starting with offshore jackets, I refer here to the Frames Joint Industry Project, which was run at the SCI in the late 1980s. Experiments were undertaken on representative tubular braced frames, and I worked on response prediction. The response of a typical frame under increasing horizontal load involves the buckling of up to 2 braces. You'll see a peak and then another drop here, and these represent the buckling of the first brace, the lower brace, and then the buckling of the upper one. 2 things to note here. Firstly, after the buckling of each brace, the resistance of the frame drops. The question is how much reserve strength the frame has that could be relied upon, and for how much deformation. Secondly, this analysis is performed with a powerful adaptive procedure that I developed. Each member is initially modeled with 1 elastic element. These are the blue regions in the structure, and these are replaced with more demanding elastoplastic elements, the red regions, when and where necessary. This typically achieves computation savings exceeding 90% in comparison with the conventional non-adaptive approach. Now, comparing against the experimental results for 2 actual frames, frame 1, where only 1 brace buckled, as predicted, perfect prediction is achieved for strength, and I should note here that these predictions were obtained in a blind manner. Not me closing my eyes. It was really the fact that the analysis was performed before the test was undertaken. And these are quite good predictions given that fact. And also, basically, we have good prediction of the post-buckling reserve strength, also within 10%. This is the buckling strength, and this is the post-buckling strength. And looking at the second frame, frame 3, where 2 braces buckled, also as predicted, strength and reserve strength were predicted well to within 10%. Now, minor discrepancies that you find here were attributed to locked forces due to the fabrication process. This led to a follow-up project subsequently undertaken at Baumel. My models were applied for a long time at Baumel in static pushover analysis of large-scale offshore jackets, and more recently in full earthquake analysis similar, but at an even larger scale to this example. This is an example of a relatively simple jacket under an earthquake signal. Successful validation as well as computational efficiency were both essential for this large-scale application of my models in practice. Looking now at buildings under fire, several experiments were conducted in the early 90s by BRE and by Chorus on a full-scale 8-story building at Cardington. These tests were motivated by the need for a performance-based approach to structural fire engineering. In parallel, we undertook 2 EPSRC projects and collaborated with the University of Edinburgh on another project, where the main focus was the development of response prediction models. Here I show a substructure model of the fire compartment for one of the tests. The temperatures in the internal secondary beam, this one, and on the lower part of the slab were highest in the test, and they ranged between 900 and 1000 degrees centigrade. Just to show you an animation of what we predicted in the analysis. Basically, we predicted deflections of around 42 centimeters at around 100 minutes. The results show good comparison between experimental results and our predictions. Minor discrepancies are due to limited temperature measurements and related approximations. Importantly, the results show that the relatively large deflections are due to restrained thermal expansion, more than a deterioration in the strength of the steel beam or the slab. In principle, the slab can support huge loads through membrane action if it has sufficient ductility. Therefore, what is ultimately important is predicting the ductility limit, which was not reached by most of the Cardington tests. This has led to follow-up research that we've been undertaking on the failure of floor slabs, as I discuss next. Now, our work was the first to consider structural failure of floor strips by reinforcement fracture. With funding from BRE, we extended this work to full floor slabs, providing simplified models that account for the important influences of bond strength, stress-strain response and ductility of the reinforcement, and the slab boundary conditions. Ahmed Al-Ghazuli and I are currently validating our response prediction models via an EPSRC project. Now, what I'll show you is a video now in fast playback of one of the experiments where major cracking of the slab can be observed. You'll observe some major cracking along the diagonals of the slab. Now, you would also have seen a Catherine jumping on the rig. Now, this is a technique that we have pioneered here at Imperial College, and to achieve very good predictability. Although we can achieve better predictability even by bashing the computers, I'm not allowing this because I chair the computing committee. So these results have been, what I'm going to show you, these have been obtained in the normal computer-friendly way, but including jumping on the rig. So this is the test result, and this is what we predict with adaptive. This is the nonlinear response, and actually it is quite good. And this is what we predict as well with our simplified models. We are now in the final stages of this project, where the models are being calibrated with observed and most representative values of bond strength for different types of reinforcement. Upon completion, we expect our calibrated models to predict the ductility limit with good accuracy, hopefully. Now, my final validation example relates to a non-conventional structural system. It's basically blinding. Blinding is the layer of unreinforced concrete used to protect the base of a cut and cover excavation. The structural use was ignored until Alan Powderham at Mott MacDonald introduced them as struts in his observational method. In collaboration with Alan, we have been studying experimentally and analytically the upheaval buckling of blinding struts through an EPSRC project led by Robert Volon and involving Dave Potts and myself. Basically, this is, I'm not sure whether you can see this properly, but this is the cut and cover excavation, and these are basically, this is the blinding, and the idea is to use them as struts to restrain the retaining walls. So the key issue here is the upheaval buckling of these blinding struts. The upheaval buckling of a blinding strut involves it buckling against its own weight. This process is very sensitive to out-of-straightness imperfections. Unlike Euler buckling of a column, the upheaval buckling for an elastic strut becomes infinitely large as the imperfections reduce to zero. We undertook preliminary static analyses of small-scale blinding struts where typical responses for two thicknesses are shown. These static analyses predicted snapback response, as you can see here. This is the buckling, and this is the snapback behavior, which meant that the actual behavior under axial loading was going to be explosive after buckling. This is a video of one of the tests, and you need to watch very closely because almost nothing happens until suddenly we get this explosive behavior. The surrounding protection was included for health and safety, obviously, after we predicted the explosive behavior, and it was indeed required. Evidently, our models can predict the response of the blinding struts accurately up to the buckling load. However, the accuracy of the prediction depends on knowledge of the imperfection, that is the ground profile, and the eccentricity of the axial load, particularly for buckling modes extending to the ends of the strut. Another issue is that there is no need in this case to consider the real post-buckling strength. The snapback energy is sufficient to break the concrete slab, reducing its real post-buckling strength to zero. And now I come to the final part of my lecture. So far, I focused on the development and validation of detailed finite element models for civil engineering structures. Simplified models are less elaborate, but have several relative benefits, including ease of application by means of hand calculation or spreadsheets. They are normally adequate for preliminary assessment, and often they are sufficient in the presence of uncertainty in the load and in the structure. But perhaps the most important benefit is their explicit formulation, which provides the engineer with a direct appreciation of cause and effect and the main parameters influencing the nonlinear response. While feasible, simplified models are relatively challenging, and they are more problem-specific than detailed finite element modeling. So a significant part of my recent work has been directed towards simplified models that can be applied in design practice, such as models for the failure of slabs by reinforcement fracture, which I mentioned very briefly before, steel beams and damaged columns under fire, steel members under blast loading. This is work that I've undertaken for the Fire and Blast Information Group at the SCI, and which is currently being applied in design practice, and simplified progressive collapse assessment of multi-story buildings, work that we've undertaken in close collaboration with ARAB. I'll focus my remaining discussion on the last type of model. The events of 11 September 2001 raised many questions about the role and responsibilities of structural engineering. I've already argued that structural engineers cannot design for unpredictable events, such as due to terrorist and malicious actions. However, engineers have to ensure that local damage does not progress to disproportionate collapse. In other words, engineers have to design structural robustness. By definition, the extreme event causing local damage is not previously and not precisely known. Otherwise, it would be designed for explicitly. What is known is that these events are typically dynamic and short duration, such as blast or impact causing local damage to a load-bearing structural component. One of the areas where we focused was the ability of a multi-story building to withstand sudden column loss, which we identified as a suitable event-independent scenario for assessing robustness. We developed the first coherent performance-based approach in which the failure of the floors above is defined in terms of the maximum displacement exceeding the ductility limit, typically in the connections. This defines a limit state for progressive collapse assessment, which recognizes the full benefits of ductility under dynamic actions. Towards this end, I proposed a multi-level assessment framework, which can be applied at the level of the full structure, the affected bay, as you can see in this case, with suitable representation of the boundary conditions, the affected floors, provided the columns can take the distributed load, a single floor if all the floors are identical, and individual beams if membrane action can be ignored or is to be ignored. If the conditions of model simplification are not met, our approach still recognizes the benefits of working at the lower levels of idealization. Indeed, the response at the higher levels can be easily assembled from the responses at the lower levels, as illustrated here schematically. Now, the proposed framework allows the nonlinear static response of the structure or relevant substructure to be determined relatively easily, but the actual response under sudden column loss involves dynamic effects which should be considered. In this respect, I propose a simplified dynamic assessment method which transforms the static response under gravity loading to a dynamic response reasonably accurately. The idea is based on energy balance between the external work and internal energy. When the column is suddenly lost, the effect is very similar to the gravity load being applied suddenly to the damaged structure. Basically, the displacements increase as the work done by the suddenly applied load, which is the red area, exceeds the internal energy absorbed, which is the green area. And the structure reaches the maximum dynamic displacement when the external work equals the internal energy. This dynamic displacement is typically much larger than the static value. Now, plotting the maximum dynamic displacement against the gravity load provides the dynamic response, which is what I also call the pseudostatic response for some technical reasons. Now, the maximum gravity load that the structure can take following sudden column loss without initiating progressive collapse is one which does not lead to dynamic displacements exceeding the ductility limit. This simplified approach was thoroughly verified against detailed finite element analysis. And in working on sudden column loss, we saw it in the main as an event-independent scenario that provides a standard test of structural robustness for multi-story buildings. However, recent work that I've undertaken has shown that this scenario is indeed very useful in design since it presents an upper bound on the floor damage. When a column is subjected to actual dynamic actions, for example, blast, the resulting damage in the upper floors is typically less than this upper bound, converging to it in the limit as the action becomes more and more extreme. We also applied our proposed approach to typical steel composite buildings and found that these can be rather vulnerable to progressive collapse. However, improved robustness may be realized by incorporating and accounting for planar floor restraints, which could enable things like compressive arching action, tensile catenary action, and or membrane action. Additional reinforcement in composite connections and detailing for enhanced ductility, and masonry infill panels. Now, where masonry infill panels are used, their contribution is not normally considered at the level of the overall structure. However, we have shown that their contribution under sudden column loss can be very significant and may provide for better structural robustness. More generally, our proposed framework offers a powerful design-oriented approach which combines ductility, redundancy, and toughness, which is the energy absorption capacity, in a single rational measure of structural robustness. This has been recognized widely and has led to the initiation of several collaborations with European and international researchers. At the end of my lecture, I return to the starting point. The structural engineering practice is about designing order in the face of chaos. And I leave you with the thought that, just like science, the role of computational mechanics and engineering research is to find order, to make order out of chaos, enhancing the possibilities for engineers to make structures safer and more predictable. I hope I have shown that my work has made a contribution towards this work. I also hope that you've managed to find some order in my talk. And if I can conclude with a few acknowledgments, I was fortunate to receive throughout my career the invaluable support of Professor Patrick Dowling, who appointed me as a lecturer in 1990, and my head of section, David Smith. I also gratefully acknowledge the support from heads and leading figures of the department, the valuable collaborations with departmental colleagues, with other academic colleagues in the UK and outside, and with key persons in the structural engineering profession. I also acknowledge the dedication of several PhD students and postdoctoral associates who helped me stretch the boundaries of order already or are doing so at present. And finally, on a personal note, my gratitude goes to my parents for supporting my education during very difficult times in Lebanon, and also for instilling in me musical interests, which are greatly appreciated and enjoyed by my friends. I'm also grateful to my family for bearing up with me over the past few weeks while preparing this lecture. My wife, Hala, takes a lot of credit for my achievements, and I'm not just saying that because I need her to drive later tonight. Thank you very much.
Well, thank you very much for that, Bassam. I'm delighted that I'm now able to call on Professor Patrick Dowling, who, as you saw earlier, is chairman of the British Association for the Advancement of Science. But perhaps more importantly, he's a former head of the Civil Engineering Department here at Imperial, and especially importantly in tonight's context, he's the person that had the foresight to appoint Bassam to his first lecturing position in the department. So Patrick, can I invite you to deliver your vote?
Well, Mr. Chairman, distinguished guests, Professor Izzuddin, it's a delight to be here. I spent 11 years as a Vice-Chancellor, and one of the duties of a Vice-Chancellor is to listen to all the inaugural lectures. I don't think this used to be the tradition here at Imperial College. I think it's long since gone. But it certainly continued at Surrey for 11 years, where it gave you a chance to understand the caliber of the people you'd appointed to chairs. Now, these were usually timed for the end of the evening, and for a Vice-Chancellor who started work at 7 o'clock in the morning, he was rather tired by the time he went down to the inaugural, and had some difficulty following some of the finer points of the inaugural address, particularly those concerned with sociology and aspects of psychology and so on, and even dance. Now, the more intelligent Vice-Chancellors devise methods to focus their attention on what is actually being said. And my system was a very good one. I insisted my personal assistant always sat beside me in the front row and gave me a nudge every time she saw me nodding off. And in particular, she would feed me with mints so that I could chew to keep awake. Now, I didn't have to do that too often, and certainly didn't have to do it this evening as I listened to the exciting and enthralling presentation we have. I really want to use the genre of a fairy story about my introduction to Bassam, whom I met 22 years ago. And if I then progress, at that time it was a very handsome head of department, like today. It was a very handsome head of department. And there you see, and he was very famous for his sartorial elegance, as you can see. At least that's the phrase I use, but my brother back in Dublin said, "You look a right gobshite, mate." And they received an application for an MSc in structural design from an almost as handsome and slightly more youthful graduate of the American University of Beirut. Please note the moustache, and any resemblance to the pack of cards that are wanted by the Americans is purely coincidental. I then, of course, as a good Vice-Chancellor would do, I talked to the registry. What can you tell me about this applicant? And at the time, I got back, he'll be okay, but it's marginal. Now, this was the prediction by somebody called Nigel Wheatley, who never gets things wrong, as I understand it. But there you are, the head of department, in a rare moment of reckless abandon and generosity. He blessed it. He blessed this occasion. This was me during my religious vocation period. And, of course, despite some serious competition within the cohort from the equally youthful Robert Vollum, who looks very old now. Where are you, Robert? Yeah. There we are. We can see the thieves. You can see Robert Vollum smiling there. He knows something good is going to happen in the future. Bassam and his other Middle Eastern colleague beside him look deeply suspicious. In that class, there were 2 first-class honours graduates from Oxford and Cambridge. You had Robert from Oxford and the young lady there from Cambridge, and they were destined definitely to get a distinction. And lo and behold, they did. But Bassam graduated top of the class and is still making history. Now here I want to correct the present head of the department. You will have been reading the newspapers about the lowering of standards in the O-level recently. And, you know, it's not the same as it was in the Golden Age. Well, when he said that the 2 people got higher marks than him subsequently, it's the same sort of phenomenon. So there we are. I suppose we'd better say something about the... unlike the registry, of course, I did recognise the talents, particularly when I saw the marks. I invited him to undertake a PhD, which he did, and he did brilliantly, with distinction. And then, as was said, I appointed him as a lecturer in structural mechanics in the care of a certain David Lloyd Smith, whom I'm told has done well as well. He's here. Well, to be a little more serious, Bassam, from the very outset, chose probably the most difficult area to do research you could do in structural analysis. He was attracted to almost intractable problems, and that is the response of structures to dynamic loading, all of nonlinear behavior, and under explosive loading, impact loading, and so on. Now, if anybody wants to get a picture of what it really is at the epitome, just think of 9/11. That was the failure of 9/11 was exactly the sort of problems, not that he had envisaged that, but the sort of problems that he went after and did. And that is an enormous challenge. And everybody was taken by complete surprise at the success he made so rapidly with his analysis. Not only was his analysis superb in predicting, as you saw there, several examples of it, collapse and residual strength of structures subjected to complex dynamic loading. But then he went on to explain how it could be much more simplified and to produce design models. So this is a rare facility in people. In my experience, I had 45 PhD students through my hands successfully. Most people either are excellent at the theory and the analysis, and very few of them have the talent to be able to bridge the gap between analysis and design and produce material that's directly useful to designers. And Bassam is one of those people. In my view, after quite a lot of experience, I would say Bassam is amongst the United Kingdom, nay, the world's best structural analyst. And we've been very privileged to hear him here this evening. I'm very proud of him. And I want you to show your thanks in the normal way for an excellent inaugural.
Thank you very much for rounding off the evening, Patrick. I see we have a new phrase now that we see that Bassam was attracted by the intractable.